Good morning, everyone. So, as I can see, I'm Adam. I'm a lecturer here at the University of Leicester and also work within NCEO. I very much look for the signal and the noise because I study aerosols and clouds, which largely are a noise term for everyone else, particularly within the thermal. And so images like this off the western coast of Australia are the types of thing I'm often interested in. So we have here on the left a variety of wispy, thin clouds that I could find very interesting to study their ice properties. On the right, we have the red soils of Australia, a unique and interesting area to look at. And in the middle, we have the annoying transitional zone, where there is certainly still cloud there, but it becomes increasingly difficult by eye to work out where the cloud ends and the surface begins. And this talk, I felt I would be going through some of the ways that we mask, identify, and deal with clouds. I'm not going to be going into the types of work I end up doing of trying to look into the properties of them, because that's not the interest to a general audience. So, by eye, we often feel that we can do a reasonable job, but that's obviously very inefficient. So, a first one, which very rarely comes up, would be a circumstance like this. So this is two different views of a scene in Alaska. So we have some clouds here at the bottom, and there's a fire through the middle. This image on the left is from the nadir, and this is from an instrument called MISR. It's a polarimeter, so it looks at 9 different angles for the scene, straight down and then off at various angles. On the right, we have made an image that's suited to, if anyone has those sort of blue and red glasses you'd get as a child to see things in 3D, we've taken the different views in the nadir and then off at 45 degrees and made one slightly bluey tinged and one somewhat red tinged. So if you wore those glasses, you would see the clouds would suddenly jump out. Because we can see down here, there's this blue blob on the left and this red blob on the right. And down at the bottom, you can see the intermingling of them. We can see that the clouds are at a different height, whereas that plume in the middle is just a sort of reddish color. The idea here is we're seeing parallax. But if we look straight down at the cloud, everything appears above where it is. But when we start looking sideways on, we co-locate the image to the ground. So all the pixels will be where they were supposed to be for the ground. But when a cloud is a couple kilometers up, when you look on at a slant angle, that cloud is now going to appear to move within the image. And so when you've got multiple views of a scene, you can use this parallax to detect clouds and potentially the height. Now, the accuracy of that is limited by the size of the cloud, its opacity, and how big your pixels are. With MISR, the pixels are several kilometers, and so it's not the most accurate thing in the world, but it can work out, and it can make these interesting little images. So this is often popular with aircraft campaigns or any circumstance where you've got multiple instruments playing with each other. And there are ideas to think about sort of small clusters of satellites, one looking on at an angle and one looking straight down, and the hope that you could try and pick out, without having to do any clever instrument design, just anything that's sensitive to a cloud, the clouds will have been somewhere where things moved. Now, that doesn't apply in general. We don't normally have multiple views. In fact, we're often dealing with lovely Landsat imagery like this over the Aral Sea, of the slow retreat of this body of water over salty and bright soils. There can be a lot of interesting things to study here, trying to pick out the smaller lakes or try and test out the extremes of a sea salt retrieval. And this is a lovely, beautiful, visible image we have here. And it doesn't seem as if there's anything in the way. But if we change our wavelength, the Landsats brought in a 1.38 micron channel to try and detect cirrus clouds. We switch to that wavelength, suddenly we can pick out there were a bunch of clouds in that scene. Flicking back, you really cannot see those ones by eye at all. Partially because they're quite thin, and partially because the surface is extremely bright. Depending on how well the screen's doing, maybe at the top you can possibly see some fingery features that then come out when the cirrus is there. But this would be the usual way that we historically try and detect clouds, of trying to pick wavelengths at which we think the cloud is more sensitive than other ones. Here, there's a lot of water vapor absorption within this band, so the idea is that a relatively small amount of cloud brings a large, bright signal in this, which is actually the opposite way around. The cloud is colder than the background, and so it's the opposite way, but cloud is always supposed to be white. So, Through careful detection, so particularly with Landsat 8, we've got this 1.38 micron channel, which is becoming increasingly common, specifically for the purpose of detecting cirrus clouds, because they are that thin one that is harder to detect by other means. Now, if you look within the image, now actually working out where things are, there might often be a thresholding technique, but that might get difficult, particularly where you see it doesn't really come out of here. There is a small amount of the surface, particularly somewhere here in the middle where you've got that saltier thing that can work. But also there are techniques about looking at the spatial covariance of the field. So if you were to take sort of like a rectangle and run it through the image on the right, as a square, and then look at the standard deviation within that. That standard deviation can provide you a second threshold in addition to just the basic threshold. So if you're stuck with only a single channel data that might be sensitive to a cloud, or you've got an image where you're trying to pull out, particularly like the difference between snow and cloud, sometimes looking at this spatial variability can matter because the surface features will usually have different scales of variation to the cloud features. Now, these aren't perfect because cloud itself has lots of different creation techniques, and so the covariability of the cloud will depend on the conditions in which it was formed and its actual cloud type. So this is difficult, but again, there's an element of a lot of this is about practically trying to move forward. Now, that's when you've just got one channel. If we get more channels, we start moving into multi-indice products. So this is a false color RGB made by EUMETSAT from Severi imagery to help people detect dust. So dust would be sand blown from the deserts into large plumes, and it's important for weather forecasting because these can get thick enough that they start interfering with the transfer of radiation. They'll block light, they'll absorb heat in different parts of the atmosphere than you expect, and change the overall circulation. These sorts of images were made to provide a qualitative view for forecasters. So this is made. This particular image is made by all of the red in the image comes from the difference between the 12 and 11 micron channels of the image. Those are supposed to physically relate to the optical depth of whatever was in the atmosphere, and it also picks out thinner layers of dust. It's not expecting to see very much from ice cloud because spectrally ice is relatively flat between 11 and 12 microns. Green is looking at the difference between 11 microns and 8.7. Here there is a gradient in ice, and so we would expect to see a larger amount of signal in this green from there being a change in the ice, whereas dust is relatively spectrally flat in the region. And then finally we just use the blue for what was the 11 micron value, which is just giving us the temperature as a whole. And this builds up then this color interpretation in the middle of saying that when we can see these blue or purpley surfaces, these are relatively dry, clean air where we're seeing through to the surface. Getting blue is telling us that we have a warmer signal, most likely the surface. Browny red is coming out as more thick, high clouds. A thick storm cloud would have a large optical depth, and then bringing in the large amount of red, but it's also got a mixture of water and ice, so isn't coming through massively in the green. Whereas these clouds here that are more mid-level and possibly quite just having more ice specifically on their own, giving us different colors in the regions. And then the pinky bit here is the dust, something picked out that's both low and warm, but also having the spectral features in the right sorts of places. And so the idea of this image, these were designed that a human trying to provide ad hoc corrections to a forecast could look at imagery rapidly. Severi gave an image every 15 minutes. More modern sensors of that geostationary type will provide 10 minutely, and you can see the movement of things around. And so in those early days, they could pick out, this is a big convective storm system, but there's also dust coming through the bottom. Because of that dust, they would expect the forecast to be inaccurate in some way, and so would provide a greater amount of uncertainty or start tweaking the forecast in ways that their personal expertise had helped them. There are a lot of these types of products, and I'd recommend if you're interested in this type of qualitative work, EUMETSAT has a website here, which is on my slides, which I'm happy to have distributed later, of a variety, there's like 20 different products like this, of false colors you can make to identify things like cloud, but there's a cirrus one, there's dust, there's snow, of various different qualitative products you can build up relatively easily if you know how to open the satellite imagery. And these can be applied to a wide variety of instruments. they're usually tuned to the specific one they've got. For example, Severi has an unusually broad channel in the thermal, which means it might be picking up bits of water vapor and things that other sensors wouldn't necessarily do. But it's often a good starting point if you're just wanting to get an idea, particularly if you're the sort of person that just looks at a small number of images for case studies, trying to go and look on this website, what's the types of things you're curious about, what are the types of things you're worried about, find a false color there, and build up those images, and you can look at them and get an intuitive sense of the type of thing you're working with. Now, if you need more numbers, we can now get into some of the other techniques. So, UMETSAT, within this Severi product, do make an operational cloud mask. There is a decision tree if you want to know how it works. I do not want you to read it now, but there's a link at the bottom. So here we have this type of dust RGB image. So we can see there's some convective cloud here forming near the equator, a more mid-level storm that's not necessarily deep convection out here in the middle of the Atlantic, but then there is a nice, lovely plume of dust coming across our image as a whole. And people online, I think, can see that moving around. Actually, does that if I go over there? Yes, there. Nice pink thing through here. The operational cloud mask is designed to run very quickly and without other inputs. It doesn't bring in meteorology. It doesn't bring in any cloud properties. It's one of the first things that they run. And here we get white supposedly being clear and orange being cloud. And we see here one of the bigger problems with the faster cloud masks. We have this giant blob of something that I would say is very clearly dust and not cloud, and it has been picked up as cloud. Because from a meteorological sense of view, it is. A dust plume is something that has a thick optical depth and a very clear thermal emitting height. It is, in a sense, a cloud. It's just not what. And so the algorithm's not wrong to flag it. It just wasn't necessarily what we were looking for. So other types of algorithm have been built. This is an example of a machine learning mask they're trialing at the moment. And we can see that the two are different, but not necessarily, and sometimes in ways that we like. You can possibly pick out where some of the training has gone. Where's my mouse? Of here, and the original operational mask was actually picking out a lot of this edge of Morocco here as cloud, but actually we're not seeing any pink there. That was just picking up the desert itself as cloud. The neural network was given a lot of training data to try and avoid that, and it's largely succeeded, provided we ignore the coast. But we also note features such as this very unphysical line coming through the middle, other features picking out, where it hasn't fixed that dust plume. So neural networks are becoming increasingly popular as a means of flagging cloud. And much as I'm a bit suspicious of neural networks as a whole, this is somewhere I think they're actually very well suited. It's a problem where there are more methods of filtering cloud than there are people that have attempted to filter cloud from satellite data. Every method will fail in some way. There's basically no perfect way of filtering cloud. And if you've come to a point in your life where it's, oh, my method is perfect, if only I could filter more of the cloud out. As a professional cloud person, I might recommend you just stop there and deal with the error budget. You're never going to be able to make this perfect, and you can lose an entire career to trying to get rid of the cloud. Because exactly, like, an interesting philosophical question is a single droplet a cloud? Maybe, maybe not. And the practical limitations you've got can matter a lot. Now, someone that I knew that did spend a lot of time on this type of thing was Ian Ashpole. He specifically wanted to be able to detect dust to save it from this cloud mask. So he built a method like this, published there, which was a relatively simple series of decisions. So something like, is the temperature at 11 microns above some threshold? Is the 12-11 difference positive? Is the 11-8 difference negative or sufficiently negative? So those were all looking at those features of that RGB product earlier. So we added specific thresholds, but then also added a variability test, looking at it if within the overall climatology, this third line was also different from its variability. So taking that qualitative image, adding some threshold and building it through, and built this lovely image, which me and some colleagues used in a paper where we were wanting to look specifically at dust that had come off. And we can see it's picking out very nicely this large plume here. It's tending to not pick out the empty desert, but it's also picking out some of the emission regions. That's never going to be perfect, and you can do similar things like this. And so if you are curious about, oh, there seems to be a lot of cloud contamination, one can build reasonable products like this, but I would also recommend you to do a deep literature search. People will have probably looked at this before, and you can do quite a lot with these threshold tests, where you tweak the threshold basically to how much noise are you willing to accept or how much you're willing to throw away. So in this case, they wanted to be able to study things they definitely knew were dust and definitely weren't wet. And so it's a relatively conservative flag from the point of view of dust, but otherwise reasonably certain that it's not cloud. And we can see that very different methods are bringing out three very different answers. So it's something here where, like, if you're looking for a cloud flag, I'd heartily encourage you to just go and take one or use one within your data, but be aware that they are going to always have weaknesses. There's going to have elements here where they might be throwing out the signal you're looking for. They might not even be detecting it at all. So taking something just out of the box as a cloud mask isn't a great idea, but I also don't think you need to read up too much about it. A little bit of actually just looking at images that you know and are used to and seeing what the features look like. If it's something from someone like UMetSat or from the ESA CCI or Copernicus, there'll be user documents designed nowadays to be like one sheet of A4, and we usually try and put within there like the, if you know nothing, know that we are bad at this. And those are usually a good place to go, just to get a feel for the types of things you might be getting wrong. There's an increasing number of neural networks around, though, and if you are going to train yours, they tend to be built off of the back of calliope, or radars or lidars in orbit. These active sensors that shoot a signal out, it bounces off of the things and come back and gives a fairly unambiguous, there was a cloud here. And when you train those types of things, so here we've got a variety of different RGBs. So this is a true color. This is the natural color we get from satellites that don't have a blue channel. And this is that dust product again. And this was from a thesis of a chap I knew named Dan, who was working on trying to improve the representation of smoke. So we can see here there's a lot of a black, milky smoke through the middle, which is different from the cloud, but in a different way to what the dust was before, and something that actually doesn't pick out of this dust RGB very well. So the types of filtering to detect smoke wasn't working. He built a binary mask like this, but actually under the hood, the neural network is usually providing some sort of number, rather than doing a direct classification with the neural network, because of the way the maths tends to work, because your training data and the thing you're working with often aren't going to have the same unambiguous. The laser is like, yes, I hit something very opaque and it came back, but it won't really be able to tell you visibly, because the infrared radiation penetrates that cloud a certain amount. It sees the cloud in a very different way. And so classifications often don't work that well. So we tend to, as a field, build something like this where we are getting a continuous quantity. In this case, something that's approximately optical depth. We don't worry too much about the exact units, but we then put a threshold on what the neural network gave us to get our mask out. And then afterwards, just comparing that to a variety of different masks, and you can see that they disagree at lots of points. So different approaches trained on different data sets with different inputs got very different answers to what was going on here. And so if you are someone interested in, like in this case, someone that wanted to study the Australian fires of 2020, that is somewhere where maybe training your own network may be valuable, because you'll get different behavior in the climatology to a specific circumstance. And here you can actually, if you choose the right sort of network, these are different bands that the instrument has done. The colors are different ways of doing it. So during the day, at night, when we've got different channels available. And you can see it picking up here, but the blue one is at night, so it's only using these thermal channels. But you can see that during the day, certain channels matter more than others, but actually all the channels of the instrument, in this case, Himawari, matter about the same. It's not caring too much about the variability, but it was there. And so that ability of using a neural network that you can pick apart and actually see what the different sensitivities were can help you to then understand how your neural network relates to maybe one of those earlier mentioned methods of channel differencing. And I thought I would wrap up at the end a bit with, like, why do we tend to care about these types of things other than just noise? Well, so firstly, if you're filtering, so in this case, this was a project between the aerosol project and the cloud project. Those of us that cared about the numbers that came out, we'd each have our own masks. The aerosol people would want things that they knew were aerosol, and the cloud people would want things that they knew were cloud. And we then looked, we were analyzing the same satellites. In theory, those two data sets should have covered the whole planet. But you will see the places where on this image it is teal or orange is where the two methods disagree. Now, orange is where they both thought it was their problem, which happens rarely. But teal is where they both thought it was the other person's problem. All the teal in this image, neither of us commented on. These transitional zones were being thrown out of both products, and they made up 20% of our observations. And so trying to fill in that entire gap was actually quite difficult, and it was just down to those subtle differences in how we'd done our flagging. And within the flag, here is the type of thing I do. So the orange is an aerosol observation, and the green is a cloud observation, and the white is where it went wrong. and so data's been thrown out. But you can see even here where I'm getting a reasonable flagging, the orangey field as you get up to a blue pixel is brightening quite a bit. That cloud, even where it isn't actually a cloud, is affecting the data. So just because you've managed to identify there was a cloud there and filtered it out, one is getting still a contamination in the vicinity of the cloud. When we pulled it apart, our interests were in aerosol cloud interactions. We wanted to look at an aerosol property and a cloud property nearby and see how the two correlated. So here on the left, we have a field of clouds, and then there's some aerosol over the top of it in a color. In the middle, we look at, well, how close is each pixel to the nearest cloud? And then we did change some filtering. And so the red bar was what was the sensitivity we saw in our aerosol if we just used all of the aerosol that was available. And we found a very strong sensitivity of a small forcing on the cloud, a small change in aerosol made a large change in the cloud, which would have significant impacts on climate change. If small amounts of aerosol could produce a large amount of cooling. Whereas when we filtered out all of the data that was very near to a cloud, in this case we used a limit of 15 kilometers, we got a much smaller limit. And the idea here was basically in the way of that earlier image, when you're near the cloud, exactly what the definition of the edge of the cloud is a bit ambiguous. If you're physically looking at it or you're using a laser, it's where there's a sharp continuity, a sharp discontinuity, a lot of particles. But the area just around the cloud is still quite moist. Water vapor fields aren't suddenly going to be sharply changed, but thermodynamics does. And so the area around a cloud is still different to that within it. It may have a different aerosol environment because of processing. It may just usually be moister. And so that element of even data where you have masked the cloud, the things around it where there isn't any cloud, where your algorithm is unlikely to find it because there isn't a strong gradient there. It is still aerosol. It's just wetter. Will also be affected. And so for the land communities, this would normally be understood as just, well, yeah, there's thinner clouds around. But when you're starting to try and look at sensitivities between different bits of the atmosphere, I think it's worth trying to spread out that thing we found in the aerosol cloud community of a warning that the cloud is a lot bigger in its influence than you might expect. So I ran through that masking clouds from image. A common first step would be those qualitative images of looking at brightness temperature differences. You can then make decision trees to form these types of masks, and because a decision tree can be automated with a neural network, those are also now quite popular. Clouds can contaminate the environment around them, but through reasonable filtering, we can come out to products like this, which is top of atmosphere long wave upwelling flux derived from Xviri, where we're not using a GERB type instrument that measures the whole spectrum. We're taking our different observations of the surface temperature over sea and land, our aerosol and our cloud observations of the atmosphere, and bringing those all together to this single view of the radiation budget coming off of the Earth for the course of it. Thank you for listening.
Do you have any questions for Adam?
Yeah.
Thank you, Adam. Very interesting talk. I have two tiny questions.
Yeah.
The first one is, if you use the 1.38 channel for retrieval of land surface temperature, then the amount of land surface temperature pixels that are left are very few. So there is an implication about, so my small question on that is how much signal in the 1.38 should there be in order for it to have an impact on the LST? And while you're thinking about that one, my other question relates to lots of pictures of aerosols over clouds, and the smoke in particular is a really good example. Can anyone do anything about this?
So for the first question, I wouldn't know a number off the top of my head, since I care more about the atmosphere. So I was getting to, so in the 1.38, there's relatively little sensitivity to the surface, but a lot of sensitivity to the water. The purpose of the channel is usually to try and flag up, here was where we think the cirrus is, and then that cirrus is going to be removing some small amount of our signal in other parts of the thermal. Of that bit of when you're looking in the 11, 12 microns, where you're getting your surface temperature from, you're going to be getting a balance of the emitting temperature of the cloud plus the emitting temperature of the surface, so you're losing some signal there. So the 1.38 is not, I wouldn't necessarily expect it to be something that you're retrieving with. You're using it as a mask to the rest of the retrieval of this is the data we think is suspect. And in those circumstances, it might be that you decide, oh, I could do a multi-layer retrieval. We're going to explicitly put some cirrus cloud in and try and actually balance the two out. But that can be difficult. That type of retrieval, though, is the type of thing of aerosols above cloud. So many.
Sorry, Simon. I just want to point out that particular channel is not designed to do any retrieval. It's really it's in a water vapor absorption line. You are only going to look at water vapor, and that's why it's at thin cirrus.
Yeah.
So you won't see any land.
Yeah, you get some of the bright land gets in there, but not in the same way you would get in the more thermal bits. So many people have claimed to be able to do multi-layer retrievals. They don't tend to be deployed at scale. So now Andy Sayer has done one using CWIFs. I'm aware of people doing it within experimental versions of the dark target algorithm on MODIS. Something like MISR or Polder are these multi-angle instruments. Those can do this much better because they can bring in that parallax, and they tend to have polarizing channels where they can actually distinguish between the round water of the cloud and the irregular shape of some of the aerosols, particularly something like smoke. Within my own retrieval, I would say it's difficult but possible. Within my retrieval, we retrieve the surface reflectors. And I've had times where I just run the whole field without filtering for the aerosol. And if I go and look at what the surface reflectance is in the cloudy areas, it does look a lot like a cloud. The retrieval has naturally, of its own accord, picked a cloud-like surface and then put some aerosol over the top of it. And so if one had a circumstance of you had a relatively homogeneous cloud field and a small amount of aerosol through the middle, it's something I keep trying to get a fourth year student to try, is what I consider to be a fun project, but they keep not taking it, where you would use the surrounding as a prior to set the cloud and then try and retrieve the aerosol over it, because that's sort of how any aerosol retrieval works. We assume a surface and then use that to ascribe the thing over the top. The surface retrievals obviously go the other way around. You assume the aerosol and try and work out the surface beneath, and you guys do better because your signal is a lot brighter than ours. But the two directions do work in the right circumstance.